Cosmic fireflies, the twinkling story of stars. Space is big, really big. It's full of amazing things like planets, comets, and galaxies. But perhaps the most fascinating objects in the universe are stars. These giant balls of burning gas are scattered throughout the cosmos, lighting up the darkness and serving as crucial building blocks for everything we know. Stars are not just pretty lights in the night sky. They are dynamic, evolving entities that undergo incredible transformations throughout their lifespan. Think of them as cosmic fireflies, each with a story to tell. Their stories are about life, death, and the amazing forces that govern the universe. From their birth in stellar nurseries to their explosive deaths as supernovae, stars play a vital role in the grand cosmic drama. Understanding their life cycle provides insights into the origins of elements, the formation of galaxies, and the ultimate fate of the universe itself. So, buckle up as we embark on a journey to explore the fascinating world of stars, focusing on their dramatic demise and the formation of one of the most enigmatic objects in the universe, the black hole. Stellar nurseries, where it all begins. Stars, like everything else in the universe, have a beginning. They are born from vast clouds of gas and dust, known as nebulae. These nebulae are like cosmic nurseries, filled with the raw materials needed to create a star. Imagine a giant cloud of hydrogen and helium, remnants from the Big Bang, the event that kick-started our universe. Over eons, gravity, the invisible force that pulls everything together, draws these particles closer and closer. As the cloud collapses, it begins to spin, and the material at its center gets incredibly dense and hot. This hot, dense core is the protostar, the earliest stage of a star's life. You can think of it like a cosmic pressure cooker. As more and more material falls onto this core, the temperature and pressure increase dramatically. Eventually, the temperature and pressure in the core become so intense that nuclear fusion ignites. This is the moment a star is truly born. The core starts converting hydrogen into helium, releasing an enormous amount of energy in the process. This energy pushes outward, counteracting the inward pull of gravity. The balancing act. A star is born. With the onset of nuclear fusion, a star enters a state of stellar equilibrium. This is a delicate balancing act between two powerful forces, gravity pulling inwards and the outward pressure from nuclear fusion. Think of a balloon. The air inside the balloon pushing outward represents the energy from nuclear fusion. The elastic skin of the balloon pulling inward represents gravity. When these forces are balanced, the balloon, like a star, remains stable. This state of equilibrium defines the star's life on the main sequence, which is like the star's adulthood. Our own sun is currently in its main sequence, happily fusing hydrogen into helium and providing us with light and warmth. The length of time a star spends on the main sequence depends on its mass. Massive stars are like gas-guzzling SUVs, burning through their fuel quickly and living short, brilliant lives. Smaller stars, like our sun, are more fuel efficient and can shine for billions of years. But no star can sustain nuclear fusion forever. Eventually, the star will run out of hydrogen fuel in its core. This marks the beginning of the end of a star's life, setting the stage for a spectacular demise. Main sequence, stellar middle age. During its main sequence stage, a star is in a state of relative stability. It's a time of steady hydrogen fusion, where the star shines brightly and consistently. Think of it as the star's middle age, a period of calm before the inevitable changes of old age. The length of a star's main sequence lifetime is inversely proportional to its mass. Massive stars, with their greater gravitational pull, experience higher core temperatures and pressures. This leads to a much faster rate of nuclear fusion, causing them to burn through their hydrogen fuel much quicker. On the other hand, smaller stars like our sun are more economical with their fuel. They have lower core temperatures and pressures, resulting in a slower rate of fusion and a much longer lifespan. Our sun, for example, has been fusing hydrogen for about 4.6 billion years and has enough fuel to continue for another 5 billion years. Section 5. Red giants. A star expands. As a star exhausts the hydrogen fuel in its core, the outward pressure from fusion decreases. Gravity, always relentless, starts to gain the upper hand. The core begins to contract under its own weight, heating up even further. This heating of the core has a dramatic effect on the star's outer layers. The increased energy output from the core causes these layers to expand dramatically, ballooning the star into a red giant. Imagine a campfire. As the wood at the center burns hotter, the flames spread outward, engulfing more fuel. During the red giant phase, the star's appearance changes dramatically. Its surface temperature cools, causing it to emit a reddish hue, hence the name red giant. These stellar giants can swell to hundreds or even thousands of times their original size, engulfing any nearby planets in the process. Section 6. The Iron Crisis, the beginning of the end. Inside the core of a red giant, a dramatic transformation is taking place. As the core contracts and heats up, it becomes a cosmic furnace, capable of fusing helium into heavier elements like carbon, oxygen, and eventually, iron. Each stage of fusion releases energy, temporarily counteracting the relentless crush of gravity. However, fusing iron is different. Iron is the most stable element in the universe, and fusing it requires more energy than it releases. This creates a critical problem for the star. With no more energy being produced in the core to counteract gravity, the star's fate is sealed. The core, now made mostly of iron, can no longer support its own weight and begins to collapse in on itself. Section 7. Supernova, the explosive death of a star. The collapse of the iron core happens in a fraction of a second, triggering one of the most violent events in the universe, a supernova explosion. Imagine a building imploding on itself, but on a cosmic scale, releasing more energy in a brief moment than our sun will emit in its entire lifetime. As the core collapses, it reaches incredible densities, forcing protons and electrons to combine and form neutrons. This neutron core acts like an ultra-dense wall, causing the infalling material from the outer layers to rebound outwards with incredible force. This rebound creates a shockwave that blasts through the star, ripping it apart and ejecting its outer layers into space at incredible speeds. This explosion is so bright that it can outshine an entire galaxy for weeks or even months. Section 8. Stellar remnants, neutron stars, and black holes. After the dazzling display of a supernova, what's left behind? The fate of the stellar core depends on its mass. If the core is relatively small, about 1.4 to 3 times the mass of our sun, it becomes a neutron star. Imagine a sphere only a few miles across but containing more mass than our sun. That's a neutron star. These incredibly dense objects are like giant atomic nuclei, held together by immense gravitational forces. They spin rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses. However, if the collapsing core is more than about 3 times the mass of our sun, gravity wins the ultimate battle. The core continues to collapse indefinitely, forming an object so dense that nothing, not even light, can escape its gravitational pull. This is a black hole. Section 9. Black holes, gravity's ultimate triumph. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are formed from the remnants of massive stars that have undergone a supernova explosion. Imagine a place where the fabric of space-time is infinitely curved, creating a gravitational well so deep that nothing can climb out. That's a black hole. They are regions of mystery where the laws of physics as we know them break down. Black holes are characterized by their immense density and gravitational pull. They have a point of no return called the event horizon, beyond which nothing can escape. Anything that crosses the event horizon, whether it be matter or light, is trapped forever. Section 10. Peering into the abyss, studying black holes. Black holes are invisible to telescopes that detect light, X-rays, or other forms of electromagnetic radiation. However, their presence can be inferred by observing their effects on nearby matter. Imagine a whirlpool in a river. You can't see the whirlpool itself, but you can see the water swirling around it, being pulled inwards. Similarly, astronomers can detect black holes by observing the behavior of stars and gas clouds orbiting around them. As matter falls into a black hole, it forms an accretion disk, a swirling disk of superheated gas that emits intense X-rays. These X-rays can be detected by space telescopes, providing evidence of the black hole's presence. Section 11. Conclusion. The cosmic dance of life and death. The journey from a star's birth to the formation of a black hole is a testament to the incredible forces at play in the universe. It's a story of cosmic cycles, where death and destruction pave the way for new beginnings. The elements forged in the hearts of stars, and during their explosive deaths, become the building blocks for planets, moons, and even life itself. We are all made of star stuff, connected to the cosmos through these stellar furnaces. Black holes, once thought to be cosmic oddities, are now recognized as fundamental components of galaxies, shaping their evolution and influencing the distribution of matter throughout the universe. As we continue to explore the cosmos, we gain a deeper appreciation for the interconnectedness of everything in the universe. From the smallest atoms to the largest black holes, we are all part of a grand cosmic dance of life, death, and renewal.